Hello, welcome back to another video. Today we're going to be talking about rational functions. We'll start off with the definition. A rational function is a function of the form r of x equals f of x over g of x, where f and g are polynomial functions and g of x does not equal 0. All that means is that a rational function is a fraction where you have a variable in the denominator. So it could be something as simple as y equals 1 over x. So as long as you have a variable in the denominator of a fraction, that would be considered a rational function. Additionally, g of x cannot equal 0, g of x being in the denominator. You cannot divide by 0, okay? A little trick that I like to remember is that 0 on the top is okay, but 0 on the bottom is a no-no. You cannot divide by 0 because it'll give you an undefined value. Okay, so you can't divide by 0 at the bottom. Or maybe I should rewrite that. Hold on. Let me say it another way. That'll be more clear. Your denominator cannot be 0. Okay. So there's going to be a lot of key features that exist in a rational function. A first type of feature will be a horizontal asymptote. And for that, you're going to be looking at the exponents. The exponents are the little numbers behind the variables. I know sometimes you guys confuse them, so I'll put it here. The little numbers behind the variables. Okay, and there's 3 acronyms that are going to help you remember when you have a horizontal asymptote. So that's BOBO, BODEN, and EATS-DC. I know they sound funny, but if you remember them, they're going to help you. BOBO stands for bigger on bottom, y equals 0. BODEN, bigger on top, there is no horizontal asymptote. And EATS-DC stands for exponents are the same, so you're going to divide the coefficients. Now, the coefficients are the numbers in front of the variables. Okay, so don't get the exponents and the coefficients confused. It's a common mistake. So the exponents are behind, the coefficients are in front. Okay, another type of feature are holes. Another word for holes is removable discontinuities. Those 2 words mean exactly the same thing. And all a hole is a break in the graph. And that occurs when there's a common factor between the numerator and the denominator that eventually cancel out. So to find the x-coordinate, whatever you cancel out, that common factor, you're going to set it equal to 0 and solve for x. To find the y-coordinate, whatever you get for the x-coordinate, you're going to plug it in to the simplified function and simplify. All right, so I have narrowed down all the steps and try to make them as easy to follow so that the process flows smoothly, okay? So there are 7 steps in total. The first step is to find the horizontal asymptote, again, using BOBO, BODEN, or EATS-DC to look at the exponents and determine where the horizontal asymptote is. Okay, step 2 is to factor the numerator and the denominator. There are times when either the numerator and or the denominator are already fully simplified. In that case, you won't have to factor. But if you do have to factor, you have a few methods. You have X method, you have difference of perfect squares, or you can factor out the greatest common factor. The next step is to identify any holes in the function. So if you notice that there's a common factor and you have to cancel them out and you have to simplify the function even more, then that cancels factor creates the hole, and you can refer back to the paragraph right above this on how to find the x and the y coordinate for the hole. Step number 4 is to find the vertical asymptote. You set the denominator equal to 0 after you have simplified. So let's say setting the simplified. So when you do this, you're not going to go back to the original question. You're always going to use the simplified fraction after you have factored. And then you solve for x. Step 5, determine the domain and the range in interval notation. 6, you find the x-intercept by setting the numerator equal to 0 and solving for x. You can have more than one x-intercept. Number 7, find the y-intercept by substituting 0 into the variables of the simplified function. So basically every x that exists, you're going to replace it with a 0 and simplify. Okay, so let's start with the first example. F of x equals x minus 4 divided by x plus 4. So the first thing you want to do is look at the exponents, and you're only going to look at the exponents of the highest terms. So the highest term here is x in the numerator and x in the denominator. Notice that it doesn't really have a exponent, but there is actually an imaginary 1 on both of them. Okay, so if a variable doesn't have one, it's missing, you can put a little 1 there to guide you. Okay, so since they are the same, for the horizontal asymptote, we're going to be using HDC, which stands for exponents are the same. We're going to divide the coefficients. Now, the coefficients, again, remember, are the numbers in front of the variable. And if a variable doesn't have a coefficient, there is an imaginary 1 being multiplied in the front. Okay, so you're going to do y equals, and you always need the y equals for the horizontal asymptote. The numerator coefficient is 1, denominator is 1, 1 divided by 1 is 1. Okay, so finally we get y equals 1 for the horizontal asymptote. And I'm going to come over to this graph and draw a horizontal dashed line at y equals 1 to represent my horizontal asymptote. Okay, now for the whole, before I find the whole, I do need to factor. But notice that x minus 4 is already simplified, and so is x plus 4. So I can't factor any more than this, okay? Step 3 is to find the whole, and that only occurs when something cancels on the top and on the bottom. But these two are not the same. And I don't know if some of you guys might be tempted to cancel out these x's, but imagine that these are in parentheses, okay? So the factor of x minus 4 does not cancel with the factor of x plus 4. Therefore, this function actually has no whole, so I'm going to put none for whole. Okay, and since there's no whole, I actually can't solve for the x and the y coordinate. That's where this work would have been shown, but I'm just going to put an x since there is no whole. Okay, the next thing I'm going to find is the vertical asymptote, which again is found by setting the denominator equal to 0. So x plus 4 equals 0. Subtract the 4 on both sides, you get x equals negative 4. Okay, so at x equals negative 4, I'm going to draw a dashed line going up and down at negative 4. This will be my vertical asymptote. Okay. The next step is the domain. So the domain is the set of all real numbers except this x coordinate and this x value. So notice that they both have the x, okay? The domain is a set of all x values. So it's going to be all real numbers except these two x's, okay? Now, we don't have one of these, so we're not going to worry about that one, but we will do all real numbers except this x value. So that'll be negative infinity to negative 4. Union negative 4 to infinity. Now notice that I used parentheses. This one kind of looks like a bracket, so let me fix it. I did use parentheses because the vertical asymptote is an imaginary line that the function will actually never touch. So you never cross the vertical asymptote, so you're never equal to the vertical asymptote, so don't put a bracket, okay? The parentheses are going to be used for vertical asymptotes. All right, so for the range, it's usually every y value except this y value and except this y value. Now, there are some exceptions, so I do recommend that you graph them to make sure that that's what the range is. So we can do that now. So go to your calculator, open up a new graph. So we had x minus 4 divided by x plus 4. Okay, so you can see that the graph looks like this. And so you see that it's all real numbers, so you start from the bottom going up, and there is a horizontal asymptote at y equals 1 where we said that it would be, and nothing else seems to be happening there. So I can say with confidence that the range is from negative infinity to 1 union 1 to infinity. Okay. The x-intercept, again, you use the numerator and set it equal to 0. So x minus 4 equals 0. You add 4 on both sides, you get x equals 4. But an x-intercept is a coordinate point, right? So the x-intercept is 4. The y-coordinate is 0. So at 4, 0, I'm going to make a little dot to represent my x-intercept. The y-intercept, you replace every x and put in a 0. So here I have 2 x's. So instead of these 2 x's, I'm going to put 0 minus 4 over 0 plus 4. And this x as well will be 0, 0, 0, 0. Okay, so f of 0 equals 0 minus 4 over 0 plus 4. All the x's got replaced to 0. Okay, 0 minus 4 is negative 4. 0 plus 4 is positive 4. That divides to negative 1. Okay, as a coordinate point, that's 0, comma, negative 1. And I'm going to put that on my graph. Now I'm going to refer back to the graph we had graphed earlier in the calculator. And I'm just going to sketch it, a very rough sketch. It doesn't have to be perfect. But just make sure you're not crossing the asymptotes. So it should look something like this, going through the x and the y intercepts. And on this side, it kind of goes like this. Okay, so that is the first example. Let's go on to the next page. So here we have x squared minus 1 divided by x minus 1. So the first thing we're going to do is look at the exponents to determine the horizontal asymptote. So the power of the numerator is 2. At the bottom, there is an imaginary 1. 2 is bigger than 1, and 2 is on the top. So this would be a case of bottom. Bigger on top means none. So there is no horizontal asymptote here. Second step is to factor. That numerator is actually a difference of perfect squares, which factors out to x plus 1, x minus 1. And the denominator is already fully simplified, which is x minus 1. Notice that the x minus 1 appears both at the top and the bottom, so we can cancel it out. So we are left with x plus 1. And notice that there was nothing left in the denominator because we canceled it out. When that happens, you're going to put a placeholder of a 1. Okay, step 3 is to find the whole. You find the whole by whatever you cancel out. We canceled out x minus 1. So I'm going to grab that and set it equal to 0. I'm going to add 1. The x-coordinate will be positive 1. Now, for the y-coordinate, whatever you get here, you're going to plug it back into the simplified equation. So I only have one x. So this x will be 1 because x equals 1 in the x-coordinate. Okay, so we're going to do f of 1 equals 1 plus 1 over 1. Okay, so again, this 1 went into this x. Okay, so f of 1 equals 1 plus 1, because this whole thing is equal to f of x, right? So f of x equals x plus 1 over 1. In this x and in this x, I'm going to be putting in this 1. Okay, so f of 1 equals 1 plus 1 over 1, which simplifies to 2. So we put this together as a coordinate point. The whole is at 1, 2. And I'm going to make a little hole at 1, 2, a little open circle to represent the whole. All right, the vertical asymptote, you set the denominator equal to 0, the simplified denominator. The denominator here is 1, set that equal to 0. 1 will never ever equal 0. So if this ever happens to you where there's no variable and it's just a number, there will be no vertical asymptote. Okay, so the domain is all real numbers on the x-axis except this x value and this x value. But we don't have one of these, so we don't have to worry about that one. So we're going to do everything except positive 1. So negative infinity to 1 union 1 to infinity. Okay. For the range, it's usually all real values except the y-coordinate of the whole and except the horizontal asymptote. But we don't have one of these, so we're just going to do everything except 2. So negative infinity to 2, union 2 to infinity. All right, so for the x-intercept, you grab the numerator, which is x plus 1, and set it equal to 0. Subtract 1, you get x equals negative 1. And as a coordinate point, that's negative 1, 0. I'm going to make a little close point to represent the x-intercept. For the y-intercept, you do f of 0. So everywhere you see an x, you're going to put in a 0. So that's 0 plus 1 over 1. And you always use the simplified one, okay? So everywhere you see an x, you put in a 0. 0 plus 1 is 1 divided by 1 is 1, okay? So the y-intercept is 0, comma 1. So I'm going to put a little close point to represent the y-intercept. And now we are ready to graph so we can sketch it. When you're graphing, I do want you to use the original function. So that was x squared minus 1 over x minus 1. And you can see it does create a straight line. Also notice that you don't see the hole. Remember we had a hole at 1, 2. So that is a limitation that you need to be aware of. The calculator will never show you the hole. So you do not need to rely, you should not rely on the calculator because the calculator will basically make you forget that there's a hole. So always try to do everything by hand, factor by hand, and see if you're going to have a hole. Because oftentimes kids get it wrong when they rely on the calculator. Okay, so there is a straight line for the graph. However, there is that hole that we talked about previously. I know mine looks a little crooked, but that's okay. So that is question number 2. Okay, moving on to question number 3. So we'll start off by looking at the exponents of the highest variables in each the numerator and the denominator. So here in the numerator we have to the power of 1, in the denominator the power of 2. 2 is bigger than 1, 2 is at the bottom, so that's Bobo, bigger on bottom. And that last O stands for y equals 0. Okay, bigger on bottom, y equals 0. So I'm going to go to my graph and make a dashed line at y equals 0 to show my horizontal asymptote. Step 2 is to factor. X plus 5 cannot be factored anymore, so I'm just going to rewrite it. But that denominator can be simplified, and I can use X method for that. Okay, so remember A times C goes in the top. So A is 1, 1 times 20 is 20, B is positive 9, and on the sides we have X and X. So what two numbers multiply to positive 20 but add up to positive 9? Those two numbers would be 4 and 5. So 4 times 5 is 20, 4 plus 5 is 9. So my two factors in the denominator will be X plus 4 times X plus 5. Now notice that X plus 5 appear in both the numerator and the denominator, so they cancel out. And since there's nothing left in my numerator, I'll put the little 1 as a placeholder, and the X plus 4 that appears in the denominator, I am leaving it in the denominator. Okay, you cannot simplify it more than this. Please do not try to get rid of the 1 in the top. Okay, step 2 is to do the whole. So the X coordinate, you grab the canceled factor, which was X plus 5, set it equal to 0, subtract 5, you get X equals negative 5. Whatever you get there, you're going to put this over here. So 1 over negative 5 plus 4. So f of negative 5 is equal to 1 over negative 5 plus 4. And then you just simplify that, okay? So 1 over negative 1, which equals negative 1. So the whole is at negative 5, negative 1. And I'm going to go to my graph and make a little hole there at negative 5, negative 1. Okay, moving on to the vertical asymptote. Whatever is left in the denominator, you set it equal to 0. So x plus 4 equals 0. subtract 4 on both sides, you get x equals -4. And then you can go to your graph and do a vertical dashed line at -4. And they're dashed because remember the asymptotes are imaginary lines. You don't really see them. Okay, so the domain is all real numbers except this x coordinate and this x value. So except these two x values. And you want to do them in increasing order. So notice that -5 is smaller than -4, so that one will come first. So it's going to be -infinity to -5 union -5 to -4 union -4 to infinity. This domain is longer than the previous examples because this one has 2 discontinuities. The first example and the second example only had one. It either only had a hole or it only had a vertical asymptote. But when you have both vertical asymptote and hole, your domain becomes longer because there are more discontinuities in the graph. Okay. Now the range is usually every y value except this y value and this y value. So let's double check it in the graph because there are exceptions to this rule. So I'm going to graph x plus 5 divided by x squared plus 9x plus 20. Okay, and we get a graph that looks like this. Again, you don't see the hole, but we can confirm that the horizontal asymptote is in fact at y equals 0. So I'm going to come back here, and so -infinity. So everything except these y values, except y equals 0 and except y equals -1. But -1 is smaller than 0, so I'm going to put the -1 first and then the 0. Okay, so that is what the range looks like. So the x-intercept, you grab the numerator, which is 1, and set it equal to 0. Like we discussed earlier, 1 does not equal 0. When that happens, there is no x-intercept. For the y-intercept, you do f of 0, and everywhere you see an x, you're going to replace it with a 0. In the simplified function, there was only one x, so I replaced that x with a 0. You get 1 over 4, which as a coordinate point would be 0, 1/4. Okay, so at 1/4, there will be a little dot to represent the y-intercept. Okay, and we can use our sketch from earlier to kind of sketch it very roughly on the graph. And again, do not cross the asymptotes. This one gets really, really close, so just be careful that you don't cross them. Okay, so that's a very, very, very rough sketch, but that gives you an idea of what the graph looks like. Okay, so this is example number 3. Okay, let's move on to the next example, example number 4. So you start with the horizontal asymptote, so always compare the highest terms. So we got a power of 2 on the top and on the bottom. So that means that the exponents are the same. You're going to divide the coefficients. The coefficient in the numerator is 2. In the denominator, there isn't 1, so you can put a little 1. So y is 2 divided by 1, which simplifies to y equals 2. Okay, so at y equals 2, I'm going to make a dashed line. That is the horizontal asymptote. Okay, now let us factor. We do have to factor both the top and the bottom here. Okay, so I'm going to use x method for both of these. And you can only use x method when you have an x squared term. If this was not here and you only had these two, x method would not be an option. Okay, you need to have the x squared term be the highest term that you have. It also doesn't work if you have x cubed. Okay, it has to be x squared. Anyway, so for the numerator, A times C, that's 2 times 1, which is 2. B is -3. And when your A is higher than 1, you do have to put 2x or whatever A you have in the bottom, okay? So what two numbers multiply to 2 and add up to -3? Those two numbers are -1 and -2, okay? So two negatives make a positive. So -1 times -2 is +2, but if you add them, you get -3. Now, you always want to observe these numbers here to see if you can simplify them. So -1/2 does not simplify, but -2/2 does. And that gives you -1. So you're going to simplify that. So in the numerator, we have 2x minus 1 divided by x minus 1, okay? Now I'm going to do this again for the denominator. So A times C is -12, B is -1, and there is the A equals 1 here, so you don't really need to put a number at the bottom, okay? So what two numbers multiply and add up? That would be -4 and +3, okay? So those two factors, I'm going to rewrite them here, x minus 4, x plus 3. Now, notice that nothing canceled out. That is a possibility that nothing cancels. So if nothing simplifies and nothing cancels out, remember that means that there is no whole. So we're going to put none there, and I'm going to be crossing out the x and the y coordinate because it doesn't exist, because there's no whole, okay? For some reason, when I printed this out or when I made my document, the domain ended up coming down here at the bottom, but I'm going to write it back at the top where it was meant to be. And I'm going to write my y-intercept a little lower because I'm going to need the space for this one. Okay, so back to the vertical asymptote. You grab your denominator and set it equal to 0, okay? X minus 4 times x plus 3 equals 0. When you have two factors that are being multiplied and set equal to 0, you actually separate them and set each one individually equal to 0, and that'll help you get x, okay? So add 4, you get x equals +4. Subtract 3, you get x equals -3. Yes, it is possible to have more than one vertical asymptote. So I'm going to draw two dashed lines at +4 and -3. Okay, so these two lines represent my vertical asymptotes. Okay, moving on to the domain. So all real numbers except this x value and this x value. We don't have one of these, so don't worry about this one. But we do have two vertical asymptotes, so it's going to be all real numbers except -3 and +4. And remember, you have to do it from smallest to greatest. So all real numbers except -3 and +4. -infinity to -3, union -3 to 4, union 4 to infinity. Okay, for the range, again, it's usually every y value except this one and that one, but there are exceptions, so let's go check the graph and make sure that that's what it is, and if it's not, then we'll fix it. Okay, so 2x squared minus 3x plus 1 divided by x squared minus x minus 12. Okay, now notice that this one is different. There is literally a bunch of graph missing between the bottom half of the graph. Whoops. Between this little part of the, oh my gosh. Anyway, so that little parabola in the middle and the other lines at the top, there is a big break in between there. So what we're going to do is figure out what the highest point is. So remember, when the graph changes from increasing to decreasing or vice versa, that creates an extrema. So that little parabola at the bottom is actually a type of extrema. It is a local maximum. So we can use our analyzing features on the calculator to figure out what that value is. So we're going to do menu, analyze graph, and that is a maximum. So I'm going to select maximum. I'm going to drag my first dashed line just about to the left of the point in question, and then I'm going to drag it to the right until the word maximum comes up and my point that I want to find is in the middle of the shaded area. And then I'm going to let go. And then I get this point. And remember, the range is the set of the y values, so I'm not interested in the 0.751, but I am interested in the 0.01. So notice that this graph goes from negative infinity to 0.01, but it doesn't start again until the horizontal asymptote, which we said was at y equals 2. So between 0 and 2, there is no graph, there is no function. So we do have to skip that when we write our domain. When we write our range. So the range here, again, was negative infinity to that y value, which was 0.01. Now, that y value was included, so when it's included, you use a bracket, union, and it didn't start again until the horizontal asymptote at 2, and then it went up for infinity. The x-intercept, you grab the numerator and set it equal to 0. So that's 2x minus 1 times x minus 1 equals 0. Remember, you're going to be separating them to solve for x. So 2x minus 1 equals 0 and x minus 1 equals 0. We're going to add 1 and then divide by 2. You get 1/2. Here you add 1, you get x equals 1. So we have two x-intercepts. We have 1/2 and 0. And we have 1, 0. So on my graph, I'm going to put two little dots. I'm going to make them kind of small because they are right next to each other. So that's what the graph looks like. And then let's do the y-intercept where we put in f of 0, okay? Now, because this graph didn't, when we factored, it didn't simplify, we're going to have kind of a long one here. But in all of these 4 x's, I'm going to be putting in a 0 to find the y-intercept. Okay, so that's 2 times 0 minus 1 times 0 minus 1 all over 0 minus 4 times 0 plus 3. Okay, so 2 times 0 is 0. And so you get 0 minus 1, which is negative 1. 0 minus 1, negative 1. Negative 1 times negative 1 is positive 1. And then 0 minus 4 is negative 4 plus 3 is negative 12. Okay, and you can confirm that on the calculator if you want. Okay, so the y-intercept is at 0, negative 1/12. So I'm going to make a little dot really close to the origin. And then we can graph it now. So remember on the graph that we had put earlier, it kind of went like this on the sides. And then in the middle, it made like a little parabola. Okay, so this is a very rough sketch, but that's kind of what it looks like. And so you can kind of tell what I was talking about the range earlier. That notice that between here and here, there is no function. So if nothing exists there, you do have to show that in the range, which is why between 0 and 2, there was nothing in our range. So we did write the correct range. So this is the first example where the range is not the same as the other ones. This one is an exception to the rule where you only exclude that one and that one. So sometimes it is different, okay? So moving on to number 5. So for starters, we're going to find the horizontal asymptote using the exponents. So the cube is bigger than the square at the top. So this will be bottom. So there is no horizontal asymptote. Now we're going to factor. Remember, if it's x cubed, you cannot use x method. So we got to think about the other method. So is it difference of squares? No. Why? 3 is not a perfect square and neither is x cubed. So that only leaves us with the greatest common factor. So we're going to observe this and see the highest term that we can take out. This one has x cubed, this one has x squared. So the highest we can take out is x squared. If I take out an x squared, I'm left with x plus 3. If you want to double check your work, you can just redistribute it. Okay, so x squared times x is x cubed, and x squared times 3 is 3x squared. For the bottom, you can use x method. Okay, so what two numbers multiply to -3 and add up to +2? Okay, those two numbers are -1 and 3. So I'm going to write those here. X minus 1 times x plus 3. Notice that x plus 3 cancels out, leaving you with x squared over x minus 1. So for the whole, on the x coordinate, whatever you canceled out, which was x plus 3, you set it equal to 0 and solve for x. You get x equals -3. And for the y coordinate, whatever you get there, you're going to plug it back in for every x. So -3 squared over -3 minus 1. -3 squared is +9. The denominator is -4. So the whole is at -3, -9/4. Now, for reference, you could try to figure out when -9/4 is as a decimal. So I can do that here. -9/4 as a decimal is approximately -2.25. I do want you to keep your answer in fraction form, but it does help you to know that it's about -2.25 when you're graphing it. So -3 and -2.25. So somewhere right here, there is going to be a hole on your graph. Okay, moving on to the vertical asymptote, you grab the denominator, which here is x minus 1, set it equal to 0. Add the 1, you get x equals 1. Go back to your graph, make a dashed line at x equals 1. Okay, so that's my vertical asymptote. Now to the domain, every x value except this one and this one. So all real numbers except -3 and +1. The range, usually everything except this and this, but there are exceptions, so I do always want you to graph it to make sure that you're not accidentally missing something. So this one was x cubed plus 3x squared divided by x squared plus 2x minus 3. Okay. Notice that this one has a huge gap in between that lower part and the upper part. So we are going to have to break the domain to represent that there is something missing. So we can figure out what the highest value is and the lowest value on both of those ends by using the analyze feature again. So analyze graph maximum. The bottom one down here is a maximum. So I'm going to put the first line on the left and then drag it to the right. I don't know where it went. Let me do it again. So you can see that the maximum is at the origin 0, 0. Why is it going away? Okay, 0, 0. Now let's find the minimum value of the upper part. So always put it to the left and then drag it to the right. Okay, so, and we're only concerned about the y values because this is the range. Okay, so notice it goes from -infinity to 0, and then it doesn't start again until 4, and then it goes up to infinity. So if I keep zooming out, notice that this graph goes on forever. Okay, so -infinity to 0, pause, again at 4 to infinity. And at 0 and 4, those were defined points, so I'm going to be using brackets. Okay, so -infinity to 0, union 4 to infinity. For the x-intercept, you grab the numerator and set it equal to 0. X squared equals 0. To get rid of the square, you take the square root. The square root of 0 is still 0. So at 0, 0, we have our x-intercept. The y-intercept, you replace every x with 0. So that's 0 squared over 0 minus 1. Which equals 0 over -1, which simplifies to 0. So again, 0, 0 is the x-intercept and also the y-intercept. Okay, And now you can use your calculator to sketch. So the graph went something like this. Okay, and again, so for the range, we didn't have anything between, hold on. So between 0 and 4, so between here and here, notice that there was no function, no graph. So between 0 and 4, we did skip that in our range. Okay, so negative infinity to 0 and then 4 to infinity. Now you might be asking yourself, what about the whole? Remember, on the range, you just need one defined point. So even though there is a hole here, there is another defined point. So you don't actually have to break up the range right here, which that's how we were able to keep going all the way until 0. Okay, so that is example number 5. Okay, moving on to the next example. Example number 6. So we'll start off with the horizontal asymptote. So observe your exponents. The numerator has a power of 1, bottom is 2, so it's bigger on the bottom, which is y equals 0. I'm going to make a dashed line on my graph at y equals 0. Okay, I'm going to factor now. The numerator is already factored, which is x minus 6. The denominator, if you're more comfortable with x method, just remember to add the plus 0 because there's no c. But you can actually do it by greatest common factor because notice that they both share an x. So I can factor out an x and I would be left with x minus 6. Again, you can redistribute to check your work. X times x is x squared and x times negative 6 is negative 6x. Okay, so the x minus 6 cancel on the top and the bottom. Since there's nothing in the top, we're going to put a 1. The denominator is x. Okay, now for the whole, whatever you factor out, you set it equal to 0. After you get your x value, you plug it back into the simplified function. So f of 6 is equal to 1 over 6. And there's nothing else to do there, so you're done. And we're going to put that in our graph. So at 6, 1, 6, that's like somewhere right here, there's going to be a hole. For the vertical asymptote, you grab the denominator, which is x, set it equal to 0. Usually we have to solve, but this one is already basically done. It's just x equals 0, so we can go straight to the graph and plot this dashed line at x equals 0. Okay, the domain is all real numbers except this x and this x. So everything except 0 and 6. The y value is usually everything except this y and this y, but let's confirm just in case because the last two examples were different. I always want you to double check for the range. Okay, x minus 6 over x squared minus 6x. Okay, so you do see that it stops at the horizontal asymptote and it doesn't have an overly large gap like the other two examples did. So this one we're good to go as usual. So all real numbers except 0 and 1, 6. Okay, so again, all y values except these two. Everything except 0 and 1/6. For the x-intercept, you grab the numerator and set it equal to 0. 1 never equals 0, so there is no x-intercept. The y-intercept, you replace everything with 0, every x. So 1 over 0, you can't divide by 0, so that's undefined. If that happens to you and it's undefined, that means there is no y-intercept. Okay, so using the graph that we just put in the calculator, you can do your little sketch. So that goes like this. You could probably do a better sketch than I can, but it's just to get the idea. Okay, so that's what the graph looks like with the asymptotes and the whole. Okay, I'll do one more example. There are a lot of examples on the document that I gave you. I want you to try those on your own. So this is the last one I'm gonna do. So number 7, we'll start with the asymptotes. The 2 and the 2 are the same at the top and the bottom, so the exponents are the same, meaning it's etc. So you're going to divide your coefficients. The coefficients on both of these are 1. So 1 divided by 1, which is y equals 1. Okay, so I'm going to do my dashed line at y equals 1 on my graph. Okay, now to factor. Using x method for the numerator, we have a times c, which is negative 28, b is 3, a is x, or 1x. So what two numbers multiply to negative 28 but add up to positive 3? Those two numbers are 7 and negative 4. Okay, so x plus 7, x minus 4. Now let's do the denominator. So a times c is 35, b is 12. Okay, a is 1. The numbers are 5 and 7. 5 times 7, 35, plus is 12. Okay, x plus 5, x plus 7. So notice that the x plus 7's cancel, and you're left with x minus 4 over x plus 5. So the x coordinate of the whole, you find it by setting the common factor equal to 0. You get negative 7. Then you do f of negative 7, and you put a negative 7 into this x and that x. So everywhere there's an x in the simplified function, negative 7 minus 4, negative 7 plus 5. Negative 7 minus 4 is negative 11. Negative 7 plus 5 is negative 2. The negatives cancel out, giving you a positive 11 over 2. So the whole is at negative 7, 11 over 2. Okay, now we can put that in the graph, not the graph, sorry, a calculator, just to see what that equals as a decimal, because that's going to help us graph it. So that's approximately 5.5. So at negative 7, 5.5, there's going to be a whole. Okay, now for the vertical asymptote, whatever your denominator is, set it equal to 0. So it subtracts 5, you get negative 5. You can put that on your graph. At negative 5, there is a vertical asymptote. Okay, for the domain, all real numbers except this x value and this x value. So everything except negative 7 and negative 5. Okay, negative infinity to negative 7, negative 7 to negative 5, and negative 5 to infinity. Now for the range, it's usually everything except this y value and that y value, but let's graph it to make sure. So x squared plus 3x minus 28 all over x squared plus 12x plus 35. Okay, so it looks like this. So if you zoom out, there is no large gap. So the only thing that was happening was the asymptote at y equals 1. If you keep zooming out, you see that there isn't a large gap. It just kind of stops at the horizontal asymptote and then keeps going. Reminder that you cannot see the whole on the graph, so you do still have to stop at the y coordinate of the whole. So we're going to do everything except this y value and this y value. So all real numbers except 1 and except 11 over 2. Remember, even though 11 over 2 is a fraction, it is bigger than 1. Remember, it's approximately what was it, like approximately, oh man, I put my hole in the wrong spot. Whoopsie daisies. It should have been at positive 5.5 and negative 7. So negative 7, positive 5.5. Okay. The x-intercept, we take the numerator, set it equal to 0, add 4, write it as a coordinate point, that's 4, 0, and then put it on your graph as a close point. The y-intercept, you put every x and replace it with 0. So here we have 0 minus 4, 0 plus 5, which is negative 4/5. Okay, as a coordinate point, like this, on the graph, that'll be about right here. Okay, so now we can sketch it. So on this side, it kind of goes like this. And on this side, kind of goes like that. Okay. I guess on this side, it kind of went lower. Let me fix it. It should kind of go like this. Okay, so this is what the graph looks like. Okay, there is one thing I actually do want to show you before I end the video, and that is found on example number 12. So notice that the numerator actually does not have a variable. There is actually a variable there, you just cannot see it. It's actually x to the power of 0. So if we go back to our calculator, I'm going to show you what happens when you raise anything to the power of 0. So I'm going to put random numbers, okay, and I'm going to raise them to the power of 0. I get 1. More random numbers to the power of 0, I still get 1. You can keep doing this all day long. Anything to the power of 0 will always be 1, meaning that x to the power of 0 is also 1, okay? So this is technically 3 times 1, right? Because x to the power of 0 is 1. Anything to the power of 0 is 1. And 3 times 1 is 3, which is why we don't actually have to write any of this. Because in the end, 3 is the same as what was originally there. However, it does help for you to know that the exponent is 0, because then you can compare the exponent at the top and on the bottom, and the bottom one has a power of 1, which is bigger at the bottom, right? So 0 is smaller than 1, so this will actually be a case of Bobo. Bigger on the bottom, y equals 0. Now, the rest of it you can do on your own. I just wanted to show you that if you ever encounter a problem that doesn't have a variable, it's just x to the power of 0 behind it. Okay, so there are 14 more problems, well, 14 problems in total. I did 7, so you can do 7 problems to practice. And I really hope that this helped. And I'll see you in the next video. Bye.